The question here is, how does the shear stress vary across the depth in a beam with a rectangular cross-section? In answering this question, let's just first review the general shear formula for calculating the shear stress for a given shear force B at a point like point A, like shown in this picture. Here we have a horizontal beam with a trapezoidal cross-section like this. The x-axis here, it's a neutral axis. If you recall, neutral axis passes through the centroid of the cross-section, right? And the y and z axes are shown on this cross-section here. The shear stress on this vertical plane at point A due to the shear force B is given by this equation. Tau xy equals bq over izz times t, where q is the integral of y times dA over this shaded area A prime, right? Izz is the second moment of inertia of this cross-section about the z-axis. T here is the width of the beam at point A in the z direction. So in my picture, that will be the direction perpendicular to the paper. Once we know the shear stress on any one of these planes on this two-dimensional differential equation drawn around point A, then we know the shear stresses on all the other planes, because these are the complementary shear stresses, right? Also, you might remember this equation. This is the equation we use to calculate the centroid of a given section. So this integral is basically equal to A prime, which is the area of the shaded area, multiplied by y bar prime, which is the distance to the centroid of the shaded area from the centroid of the section. So this equation is valid for any cross-section. Only restriction is that the cross-section has to be symmetric about the y-axis, right? For example, my cross-section could look like this. As long as the cross-section is symmetric about the y-axis, this equation is still valid. The question is, how does the shear stress tau xy vary with y if we have a rectangular cross-section like shown in this picture? So let's go ahead and calculate some of the quantities appearing in this equation for this rectangular cross-section, starting with A prime. So A prime is the area of the shaded part, which is this distance right here, which is c minus y, multiplied by this distance, right, which is t. So c minus y times t is A prime. And y bar prime, which is the distance to the centroid from this point right here, is y plus half of the width, the height of this shaded area, which is c minus y over 2. So that simplifies to c plus y over 2. Q then is A prime multiplied by y bar prime. And A prime is this, and y bar prime is this. So you substitute those two quantities in this equation. And then you might recall that the formula that c minus y times c plus y is c squared minus y squared, right? And therefore q is simply t over 2 multiplied by c squared minus y squared. Izz is the second moment of inertia of this rectangular cross-section about the z-axis. And again, you might recall this formula, 1 over 12 times bd cubed, where b is the width of the cross-section in the direction of the axis along which we are seeking the second moment of inertia, and therefore that will be t, right? So 1 over 12 times t times the depth cubed. The depth of this beam with respect to this axis would be 2 times c. So 2 times c cubed. That simplifies to 2t c cubed over 3. Now we substitute these expressions in this equation for these quantities and simplify in order to come up with this equation for tau xy. And here we note that 2 times c multiplied by t is the cross-sectional area of this cross-section, right? So this expression can be further simplified to this. So this is the standard form that you will find in many books. So what kind of equation do we have? We have an equation of a parabola, right? And the shape of the variation of the shear stress in the y direction is this right here. All right. So you have zero shear stresses at these points, at the top of the beam and at the bottom of the beam, and the maximum occurs in the middle, right? And the maximum value is 3v over 2a. How did I find that? Well, all you have to do is to substitute 0 for y in this equation. So the second term drops, and therefore the maximum value of tau xy from this equation is 3v over 2a. So here you have it. This is how the shear stress due to a shear force V varies across the depth in a beam with a rectangular cross section.